Good afternoon and welcome to our Nuclear Engineering Colloquium series. The President and Chief Technologist of Flibe Energy, Kirk, he's also affectionately called Mr. Thorium.
If you'd have told me when I was an undergrad that I was going to be in nuclear engineering, I'd have laughed in your face. I'd have said, what are you talking about? I mean, I not only had no interest in nuclear engineering, I actually had negative interest in nuclear engineering. I would have just been I wanted to go build rockets and wanted to work at NASA. And, sometimes be careful what you wish for. You might actually get it. I did. And there was a lot of things I really loved about working at NASA. But I think what I was hoping for was a little closer to what SpaceX became rather than what NASA was back then. Originally got into space stuff because I was really fascinated by exploring space. And while I was there at NASA, I learned about this technology from a friend of mine who had actually gone to the library and found a book on it. I started learning about molten-salt reactors, and I'd never heard of such a thing. I'd never heard of thorium. I'd never heard of what this could mean, and I got very, very excited about it. Our company is called Flibe Energy, and we're working on a molten-salt reactor. It's based on the thorium fuel cycle. It's got two fluids in it, a fuel salt, and it's also got a blanket salt that surrounds the fuel salt and absorbs neutrons. You can achieve much higher nuclear efficiency capturing all those neutrons. And this is based on using liquid fuel, which is pretty different than solid fuel. But we believe this liquid fuel is really going to be the key to realizing the energy possibilities of thorium and making it possible to have an endless supply of nuclear energy. And this whole idea really starts with a thorium fuel cycle. If we start at the moment of fission, this is when the nucleus splits apart. And we need at least one of the neutrons from fission to make its way to an atom of thorium and be absorbed in that atom. And then that atom is going to decay to another element, protactinium, and that's ultimately going to decay to fissile uranium, uranium-233. And then that can be struck by a neutron, have another fission, and at least one of those neutrons is going to make its way into another atom of thorium. And so you can keep the process going, theoretically, indefinitely, which is really kind of magic. I mean, first time I learned about this, my mind was completely blown. This was even possible in real physics in our real world. So let's talk a little bit about uranium. We know it's got 92 protons, and in this case, it's got 141 neutrons, and altogether that's a mass of 233. So that makes this material uranium-233. Now, if uranium's got 141 or 143 neutrons, it has a special property. It's fissile. That means it has the ability to undergo nuclear fission. The uranium atom is also surrounded by a bunch of electrons. Uranium has 4 outer electrons that it can share with other things, in this case, fluorine. And when fluorine is bonded to uranium, that's why we call it uranium tetrafluoride. And the tetra means 4. This kind of bonding is actually really common with fluorine. This is how fluorine bonds, forming ions. You may have brushed your teeth with a similar compound of fluoride called sodium fluoride. So when a uranium atom is struck by a slow neutron, it can set up a process of fission here, and that fission erupts and it releases a lot of energy. It releases 2 fission products, but it also releases several neutrons. And these neutrons, they've got so much energy, they're moving so fast that it's very unlikely they're going to cause another fission reaction. So we got to slow them down. And it turns out that this process works really well in carbon in the form of graphite. Neutron rattles around in the graphite and it slows down and it loses energy, and then it's all set up to trigger another fission reaction here. We got to make sure one of these neutrons finds another atom of uranium-233, but let's follow the other neutron. Where's it going to go? Well, we want it to find an atom of thorium. And if it finds this atom of thorium, it's going to turn thorium into a new nuclear fuel. So natural thorium's got 90 protons, it's got 142 neutrons, and that gives it an atomic mass of 232, which is why we call it thorium-232. And all thorium is thorium-232, essentially. When it absorbs this neutron, on the other hand, the neutron count goes up 1, and all of a sudden it's not thorium-232 anymore, it's thorium-233. And it's not going to stay that way very long. It's actually going to undergo a decay process in about 30 minutes where one of these neutrons is going to turn into a proton and it's going to emit an electron. And this process is called beta decay. That's going to change the number of protons to 91. It's going to change the number of neutrons down to 142. And we are now going to have a new element, protactinium-233. Now, protactinium-233 is now chemically distinct from the thorium it was in before. It has the possibility to be extracted. We need this protactinium to decay to uranium, but we don't want it to absorb another neutron in the time it takes to do that. And it's going to take, on average, about a month for that to happen. In the meantime, we want to keep protactinium away from neutrons. We don't want it to get any more neutrons. We need to take it out, and we propose using this electrolytic cell, which is kind of basically a battery. And we would run a pretty modest voltage, about a little less than 1.5 volts between the anode and the cathode. And this would actually cause thorium to evolve off this sacrificial anode, while at the same time protactinium is being driven into a pool of metallic bismuth. And load this protactinium into a fuel salt carrier and give it time, several months, for it to decay into fissile uranium. And by the time it does this, then it's ready to be introduced back into the reactor after it's undergone this decay process. And we can load it back into the fuel, refuel the reactor this way. So we can keep this process going on and on and on if we design the reactor right and use it properly. But really the key to making all this work is that uranium-233. It's very valuable, it's very important, and we're not going to be able to start the thorium reactor without it. So this is really the starting point to the whole process here. But if we can do this, we can realize endless amounts of energy for the world, because essentially we have an endless amount of energy from thorium. It's a possibility to go from where we are today, which is using about 0.5% of the energy in the uranium in the ore that we mine, to almost 100% of the energy being utilized from the thorium in these molten salt reactors. I mean, that's practically a 200-to-1 advantage. And by so doing that, we can almost completely eliminate the production of new nuclear waste. But as they say on TV, but wait, there's more. Not only can we do that, which would be totally exciting all by itself, but we can potentially take these molten salt technologies and we can go back and we can apply them against old spent nuclear fuel. Y'all have taken fuel cycle class, right? Y'all know what happens to nuclear fuel when you make it? Take uranium dioxide, what do you do with it? That's right, you gotta make it a fluoride, very good. You gotta make it into a fluoride. So first thing you gotta do is you gotta change it into something else. Well, that's what these reactors run on, is they run on uranium fluoride. So the point I try to make to people is, talking about using uranium fluorides is not weird, it's not strange. It's actually something we do with every speck of uranium we use today. It's all been a fluoride. First it was a tetrafluoride, and then it was a hexafluoride, and then went through an enrichment plant, and then we had to make it back into an oxide again, or a metal, or something else. So what we're talking about, and we're not the only ones, we could take uranium dioxide, spent fuel, and we could fluorinate it again, just like we did in the beginning, and we could make a salt mixture. We can make a molten salt mixture. And then once we've made a salt mixture, we can potentially go and remove certain things we want to take out. Maybe we want to take out the uranium. Maybe we want to go and recycle that, because uranium is most of the spent fuel, but it's almost none of the radioactivity. So we can take out about 95% of the mass of the spent fuel just by recycling the uranium, just by recycling it back into our existing economy. But there's other things we can recycle too. We can recycle noble gases. One of them is xenon. When I was at NASA, we were very interested in xenon because that's a fuel that we use for spacecraft. In fact, a spacecraft was launched just the other day. Did anybody know what spacecraft that was that got launched? Psyche. Where's Psyche going? It's going to Psyche. That's right. Very good. Where's Psyche at? It's in the asteroid belt. What ions are they throwing out the back of that ion engine? Xenon, that's right. We used to joke at NASA, xenon was the only thing worth launching into space because it was the only thing that cost as much as it cost to launch it. Everything else was cheap. But xenon was so darn expensive that it was like actually worth launching into space because it was that expensive. Did you know xenon's the most common fission product? Did you know xenon stabilizes in about a month? So there's a shocking amount of xenon sitting around in spent nuclear fuel. That's like the #1 thing fission makes is xenon. The fission reaction is making lots of things, and I was just amazed how many of these become stable isotopes and become potentially useful. But the problem is right now is all of these fission products are mixed together in a totally semi-worthless configuration. So let me give you an analogy here. Let's say you went home. How many got a pantry in wherever you live? Food, cereal, rice, sugar, beans, kale in the pantry? That goes in the fridge. I'm going to take all this food in the pantry and I'm going to dump it in a big pile on my kitchen, okay, on the floor of the kitchen. I'm going to take my broom and I'm going to mix it in a big pile, all right? And then you look at it. What do you got? Do you have this? Has mass changed? No. You have the same amount of stuff that you had before. Has temperature changed? What's the problem now, though? Is that useful material to you? If you got your beans and your cereal and your rice and your sugar all mixed together, it's totally worthless, right? All you can do at that point is you can scoop it up and throw it in the trash can and throw it away. Because it turns out what was valuable about your pantry was that everything was separated, right? Your rice was in your rice bin and your cereal was in your cereal bin. That's how spent nuclear fuel is right now. Everything's mixed together. The neodymium and the samarium and the lanthanum and the cerium and the strontium and the cesium, it's all in a big pile. Okay? And that's what kind of makes it worthless to us right now. It's the fact that it's all mixed together. Let me tell you something really cool, though, about molten salts. If you made spent nuclear fuel into a salt, we could then use electrochemistry to tease out the various species of salts and actually extract these fission products onto electrodes. And now suddenly it's like we've unscrambled the egg. We figured out how to get individual species of materials. Now all of a sudden they're not worthless anymore. Now they're useful because I found almost every single thing that comes out of fission, if you can get it by itself, is a useful thing. If you can get the strontium, and you can get the cesium, and you can get the lanthanum, and you can get the barium, and you can get the xenon, you can get them all by themselves, every single one of them has value. What they don't have value is when they're all mixed together like they are right now. Just like your pantry wouldn't have any value if everything was mixed into a big pile. So we think that that is going to be a very exciting thing to do, not only with spent nuclear fuel, but also with the fuels for these reactors, because we want to be able to reuse and recycle all kinds of material. And fission is an amazing way to make new things, to make things that we can utilize in society and in some cases have incredibly special values. There's even a class of materials that are used in medicines because they're radioactive. I was talking to a guy the other day with a company called Xeno Power, and they're getting ready to build a battery based on strontium-90. And he was saying, oh, you know, if you're going to make strontium, can we use it? And I said, oh, heck yeah, that's great. Now we got somebody who wants it. Okay, wonderful. You know, so I think this is going to be a very exciting step forward in nuclear that we're going to see in the not too distant future. And this is why I'm really hesitant to say nuclear waste is waste. When people talk about taking nuclear waste and throwing it away, I almost want to go, whoa, don't do that too fast, because I really think we're on the cusp of figuring out how to make that stuff very, very valuable and very, very useful. And I think one of the keys to that, though, is we've got to get it into a molten salt. Once we get into molten salt, we can start to do electrochemistry on it. But right now, as a ceramic, it's just about impossible to do those kind of separations on it because just of the nature of what a ceramic fuel is like.
When I've been up talking to some of the leadership at NNSA before, you know, they're kind of responsible for the fuel kind of getting to the plant and then, you know, kind of for diversion and non-proliferation. Then when it gets out of the plant, you know, they would love to have a fuel that attaches to something that makes it worthless, that can never be separated, right?
Yep,
I mean, they would. That's like, I mean, which is the opposite of
exactly the opposite.
Exactly the opposite of what you want to do.
Couldn't be more.
But if you looked at things like TRISO, is you talked about, you know, recycling kind of our current fuel, but what about like TRISO? Can you?
Really hard to recycle.
Yeah, so they like TRISO because they think it's more proliferation resistant than our current fuel. So I was just wondering if you've ever thought about.
Oh, I've thought.
Yeah,
I've
okay.
thought a ton about. I'm tell you right now, I'm not a TRISO fan. You know, the United States has got a lot of separated weapons material. We have 30 tons of surplus plutonium. We have more than that in the existing arsenal. We have a lot of HEU. The notion that the United States is going to take spent nuclear fuel and somehow divert it, I mean, it beggars imagination. Like, we're not. Like, we literally have a pile of weapons-grade plutonium that if we want to go make bombs, we go make bombs out of it, you know? We're clearly not making bombs out of it. So I will tell people, in terms of the United States, there is no such thing as diversion or proliferation. Dude, we already have bombs. Nothing will be more useful for a weapon than the pile of weapons-grade plutonium we have sitting around surplus right now. So, do we need a TRISO? For us? No, we don't.
What kind of regulatory hurdles do you have to overcome, I guess mainly containment-wise, since you're dealing with removal of fission products, mainly gaseous fission products?
Well, you know, it's really interesting. A lot of reactors today already do have gaseous fission product handling. BWRs, had to study this when I took Dr. Miller's class. BWRs have a pretty serious gaseous fission product handling system. The difference is our gaseous fission product handling system is designed to handle the entire gaseous fission product inventory constantly. But in principle, it's not that different than what we're already doing today. I was really surprised, actually, you know, in several of the classes I took at UT to learn that a lot of our reactors today already have chemistry control. They have to deal with leakers and fuel. They have to deal with fission products going to where they're not supposed to. So, you know, there's a fair amount of some of these things already taking place in commercial industry, more than you might suspect. Our pins are not perfect. They're getting better all the time, but they're not perfect. And we do have fuel failures sometimes, and we do have to handle some of these things. As far as the NRC goes, there's definitely going to be re-education going on, but this is common for all kinds of advanced reactors are facing the challenge of trying to spool up more understanding in the NRC. For the longest time in the NRC, you could count on a bunch of guys who'd been in the Navy nuclear program going to the NRC who understood PWRs and BWRs, and it wasn't that hard. Now what we're asking the NRC to do, though, is to understand reactors where there are not existing commercial examples and there's no Navy heritage to draw on. And so I think, Wes, you've got a Navy background, right? I mean, this is going to be the thing. This is going to be a challenge, a step in the, a step in the right direction. But you're absolutely right. It's going to be something we're going to have to work on, and it's going to take time. One of the things I really am hoping, though, is there's been movement in Congress to tell the NRC that if you're working with startups or advanced reactors or new companies, that you're not going to charge their time against that kind of learning curve, which I think would be really great. Makes a lot of sense. Our current regulatory structure is built around people with big gigawatt plants that make lots of money and need fairly light regulation. We're talking about startups that need new understanding, and it's real hard to pay for that at $400 an hour. I think there's a question back there.
One of the pros of ceramic fuels and solid fuels is that you contain a lot of the fission products and damage levels a lot better. What are your plans to mitigate corrosion and damage levels in your core structural materials? Well,
I mean, there's certainly partly true to what you're saying, but I would actually make the case that we contain fission products better in the fluoride form. Fluorides are more tightly bonded to most metals than oxides are. They're more electronegative, and there are certainly certain species, cesium in particular. Cesium is volatile in oxide media, but it's absolutely rock solid stable in fluoride media. Cesium fluoride might be the most stable salt there is. So these fluoride compounds really lock down fission products very well in non-volatile forms. There are a few exceptions, obviously, like fission product gases, but that's no different in solid fuel. Solid fuel undergoes structural damage, just due to the fact that the covalent bond can't stand a multi-EV neutron, so it breaks apart. In the ionic bonding that you find in a molten salt, the bond strengths are continuously renewed. I mean, you basically bust apart the bond, it just comes back right back together again. It's the nature of an ionic bond. I think we have an excellent argument for the chemical containment of the fuel itself. I mean, the chemical containment of many species of fission products will be much better in fluoride media than they will be in oxide media, and far less susceptible to thermal excursion. We want to get it hot and actually have a meltdown and have a fission product release. Fluorides just don't get that hot before they'll radiate that heat away. So it's a great material for these sorts of problems. It doesn't contain everything, but neither does anything else. But it does have a bond that is impervious to radiation damage and constantly renewing. So that's great. I mean, it's like I said, I wish I'd have thought all this stuff up.
What do you think are the anticipated doses for structural materials in the system that you're looking at from neutron damage?
Well, that's a good question. I mean, I don't have like numbers I can throw off the top of my head, but one of the basic principles of this notion of having a fuel in a blanket is that we use the blanket essentially as an internal radiation shield. It's very good at absorbing neutrons, and it's pretty darn good against gammas too. And by so doing and configuring the reactor properly, we think we can keep the dose on the reactor vessel a lot lower than what you have in today's PWRs. In a PWR, I mean, you have some water between you and the outside of the vessel, but a lot of neutrons and a lot of gammas make it to that structural material and they degrade it. No metal really does well in neutrons. I mean, they just don't exist. Some do better than others. There's actually a huge problem for fusion. Fusion's got 14 MeV neutrons hitting the first wall, and whatever that is going to get the you-know-what kicked out of it. Fission lets you put stuff between your fuel and that structural material. Now, the one place where that process gets a little thinner, though, is in the first wall of our primary heat exchanger. And that's kind of akin to like the clad of a typical reactor. That's where you're going to have a pretty hefty dose of gammas. But because our fuel is actually outside of the neutronically active region, then you're just dealing basically with like delayed neutrons at that point as far as the neutronic flux. Whereas in clad, you're dealing with, the full blast of fast neutrons going out and thermal neutrons coming in. So it's a much harder problem. Now, of course, we replace clad, every couple of years in a reactor. You put an assembly in, it's clad, and we take it out because we don't know of a material that's going to survive that kind of neutronic flux for ever and ever and ever. We certainly haven't come up with it yet. But what I'm saying is there are possibilities in the molten salt reactor design that let you really, really, really dial down that problem, particularly for the vessel, but even for the primary heat exchanger, which is where you have the thinnest walls.
Radioisotopes for medical uses. Big thing is actinium-225. What's is there any relationship between that with U-233 and thorium?
Here's your $20 bill, Wes. Thanks for asking me that question. No, thank you. That's an excellent question, Dr. Hines. Yes, there is a relationship between actinium-225 and uranium-233. Uranium-233 will decay to thorium-229, and then that in turn will decay to actinium-225. In fact, that's one of the only ways you can make actinium-225. So by using the thorium fuel cycle and the uranium-233 fueled reactor, we can actually produce a category of targeted alpha therapy isotopes like actinium-225, bismuth-213 that would be suitable for fighting cancers. And it's really unique that way because while there are a few other potential candidates for this, they're just not near as good as this one. And it's
so many of us have probably heard about how they milk some materials out at Oak Ridge and make this 225, right? It's one of the only sources that we have. And so where does that come from?
Well, it came from the operation of thorium reactors. The source that they milk for that actinium-225 is about 0.5 gram of thorium-229. And I met the guy one time who actually went and got that 0.5 gram, and he was pretty ticked because he had been trying to save 30 grams of thorium-229 that was in a vessel and was only able to, most of the rest got thrown away before they gave him. He literally rinsed what was left in the vessel, and that's where he got the 0.5 gram that ended up on that column out there. So it's kind of a horrible story, but yeah, they're saving lives with that little tiny rinse he did. Think what they could have been doing if they'd saved the 30 grams.
So going back to the electrochemical separation of the different isotopes that are going to be dissolved inside of the molten salt, what exactly is the mechanism that you're using to discriminate against what specific atom you're collecting?
Voltage. It's the only thing you do. Voltage.
Straight voltage determines what comes out of it?
Yeah. There's an electromotive series, and you just essentially change the voltage, and you kind of go one at a time going, we're going to get this one out, I'm going to turn up the voltage, we're going to get this one out, I'm going to turn up the voltage, get this one out, And it's interesting how close the voltages are to one another, though. They're not very far off from one another. A friend of mine said, by 2 volts, you've done everything. It's just like, it's a lot shorter list than you might think. But yeah, voltage is your discriminator. That's how you go and pull things out.
How are you going to account for anything that somebody could just come in and take it? I'm sure uranium-233 is a tank full of uranium-233, or soon to be 233, is rather...
it's hot.
Well, it probably looks good to somebody that wants to commit terrorism.
It's hot on several levels. Number one, it's hot. It's like 650 degrees. Number two, it's hot. It's throwing out really hard gammas. And number three, it's inside a furnace that's also at 600 degrees. So it's not like a room you're going to walk in and swipe it. And the short answer is it's really easy to notice when it gets stolen. And we were working on a safeguards approach with Oak Ridge National Lab. Unfortunately, kind of got truncated by COVID, but we're making some really good progress on basically getting everything into sufficiently small enough packages that, number one, it's not a significant quantity, and number two, you'll detect diversion very quickly. And diversion is generally going to be lethal in this case in very short order because of the highly emissive nature of some of these decays. Didn't have time to go into some of the specifics of that, but there is a nice long answer to that, and we have a report about it, and be happy to pass that along to you if you're interested.
I was wondering if there's any, in particular, INC challenges that come with your design, and if you are planning just for commercial operations for electricity generation, or what's the business model as well?
Okay, the question was, are there INC challenges? And the answer is yes, there are. And unfortunately, because I'm not nearly as good at INC as maybe some other things, I can only guess at some of the challenges. But you're dealing with a system, like I said, it's very both radiologically and temperature hot. And that means a lot of potential instrumentation just isn't going to be able to be used in something like this. As we've gone back and studied how Oak Ridge did this in the past, there's been a little bit of semi-horror going, oh, wow, we ran a molten-salt reactor without knowing this or without knowing this or without knowing this. And so, we would definitely today want much better instrumentation and much better insight into what's going on. But there are also some very interesting alternative approaches that are being looked at. I know a guy, and his expertise is sound monitoring, and he goes, I can put acoustic sensors on this thing. I can tell you everything that's going on in there. I said, no way. And he goes, yeah. Is it like sonar? And he goes, yeah, pretty much. As far as your question about the business model, there are, as Dr. Hines was telling, there's a lot of different things you can do in molten-salt reactors. You can work on power generation, you can work on waste remediation, you can work on isotope production, you can work on process heat generation. So there are a plethora of possible valuable products that really differentiates. I like to think of them as like a cornucopia of good things, and that takes them way beyond what we've got today, where really we just make electricity. We're going to go a lot farther than that. All right.
Okay, let's thank Mr. Thorium.